Okay, we're going to give this a shot, see how it works out. Uh, we've got a little simple problem here that may illustrate some of the challenges facing solving static physics problems. Okay, we'll hope for the best. He says this is what we've got going on. What you see here is a monkey hanging from a ring attached to two ropes to the ceiling. They have some angles, theta 1 and theta 2. So the question posed is, what is the tension in the left rope and the right rope? And assuming these angles theta 1 and theta 2 to be different. So let's see what we can make happen on that. Okay, so we would first want to uh, make a free body diagram to relate the key forces that are involved here. And to do that, we would want to separate these ropes from their surroundings and replace each of these ropes where the cuts are, replace it with the action of the force that is revealed when that cut is made. So to do that, got to get the right drawing tool here. Yeah. To do that, we make some kind of a cut around here. And separate that from the environment. So we'll try to do that down here. So what does that end up looking like then? And now we'll have the tension in the left rope. Oh, we can probably do better than that. We'll just use an arrow. Sure. Tension in the left rope. Tension in the right rope. And the force that results from the weight of the monkey. So the weight is equal to mg. The force that's revealed on the left side is just the tension. We're calling this T1. Yeah, we really need to fix these. And then we'll call this guy T2. Okay, so we'll pick up where we left off. We've got the free body diagram that represents the tension revealed in each of the ropes when it was cut and separated from its environment. And we also have then the weight, the force due to the mass of the monkey hanging in a gravitational field. So now we need to write some equations in order to calculate the forces T1 and T2 that obviously will depend on the weight of the monkey. So we'll write some equations based on Newton's law for a stationary object for equilibrium that says that the sum of the forces in each direction must be equal to 0. It's a static problem. There's no acceleration. So, but first, to make that process a little easier, we want to decompose or represent each of these tensions in their x and y components. In other words, break this tension T1 down into an x component and a y component. So let's try to do that. Yeah, I'm going to have a little bit of problem with the so these two forces, T1x and T1y, would, when we add them in vector sense, will give us this equivalent or resultant tension T1. And likewise, we can do the same thing for the other direction. Let's put some labels on here before we get too far afield. So this is going to be our T1x, and we'll do a little cut and paste here, T1y. And likewise, we'll put some components on here. This one is T2. And this one is T2x. Okay, well that's nice. We put some labels there, but we really need to relate these variables T2y and T2x to the original unknown T2. That actually is going to simplify the problem, but of course that requires bringing in some trigonometry, this angle theta. So let's look over here on this side first and just recall that this angle, oops, I'm not able to steal that out of there. Maybe I can do it this way. Yeah, I think I liberated it. That's the angle theta 1 in there, and the angle theta 2 is in here. Okay, so the way we're going to break these down is using the simple trigonometry laws that says the opposite side from angle theta over the hypotenuse is the sine of this angle, and the other relation, that the adjacent side over this hypotenuse is the cosine of this angle. So T1x, let's see if I can recover this. So this is equal to T1 times the sine of theta. And I'm going to have a bigger box there. Let's see if we can fix that. There we go. Okay, and likewise for this vertical force, its magnitude, I can anticipate I need some more help there. And again, we'll do a little copy and paste here. That's T1, but this is not sine, this is going to be cosine. And likewise, these values over here have the same relationship. But now we're talking about cosine theta 2. And I'll just type this one out maybe. Well, I'll cheat. Copy this off of here. But make sure I tell it that this is T2 sine theta 2. Okay. So the opposite over the hypotenuse is the sine, and the adjacent over the hypotenuse is the cosine. And that's what we have here. Okay, so now we've got the vectors broken down. And I guess we'd put a little squiggle in here to let us know that we've replaced these with the equivalent forces. So T1, T2, we've broken that down into those equivalent forces. So now we're ready to apply the principles, sum the forces to determine the equations that we need to solve to come up with T1 and T2. Let's see if it can happen. Somewhere in here, need to, well, we'll just, no. Okay, so we're ready to write the equations to solve for the tensions T1 and T2. And we want to first sum the forces in the horizontal or x direction. We'll take x direction positive to the right. So if we sum those forces in the x direction, we'll see we have T2 sine theta 2 in the plus x direction and minus T1 sine theta 1 in the minus x direction. That has to add up to 0. So that doesn't tell us T1 or T2, but it does allow us to tell us something about T1 in relation to T2 or T2 in relation to T1. We need another equation because we still have two unknowns, but we can sum forces in the y direction as well. So if we sum forces in the y direction, we see that T1, again, take y positive upwards. It's arbitrary, but we can take y positive upwards. T1 cosine theta 1 plus T2 cosine theta 2 minus the weight, which is mg. That has to add up to 0. So now we have two equations, equation 1.2 and equation 1.4, with two unknown variables, T1 and T2. So if we solve equation 1.2 for T2, and then we can substitute that into equation 1.4, then we can arrive at an answer. Solve this out for the T1. We take sine theta 2 over cosine theta 2, that's tangent theta 2. So we end up with an expression like this for T1, and then if we solve for T1, we can go back to equation 1.2 to find, or rather equation 1.5 to evaluate T2. So without putting any numbers here, that's how it works out. So that's the end of the example.